All right, in this unit, we're going to get into a discussion of, well, based on the title, definite integrals, but also a fundamental theorem of calculus, which allows us to evaluate definite integrals. So, yeah, I mean, you can read the blurb here, but basically we're talking about area. All right, so area in a bounded region. So, I took the liberty of drawing several arbitrary curves, what I call arbitrary curves, over an interval from A to B. And what I'm going to do is I'm going to take a little time and just illustrate what each one of these properties actually represent when we're really just kind of investigating this concept. Fundamental theorem of calculus part 1 is a little bit easier to understand than part 2. Part 2 kind of has its own day in the sun, I guess. So we'll kind of put that off a little bit for, I was going to say later, but probably a future video. So integral on the interval from A to B of the function f of x dx is equal to capital F of B minus capital F of A, which is really just telling us that we're taking the antiderivative of the function f of x and substituting the upper bound and then substituting the lower bound and then subtracting the two. And what you're going to get is an area. All right, and so I'm going to highlight the two. So f of b is going to be all of this area. Right, so bounded between the function and the x-axis, and also between the line x equals b and x equals 0. All right, so it's bounded in 2 dimensions. F of A is going to be, so if I denote that, I almost said demark that, I don't even know, I'm making up words now. This interval x equals A, and also x equals 0. All right, so those two bounded regions are now being subtracted from one another. And what we learned way back in Algebra 1, is that if you wanted to find the distance, the area between two interval or regions, find the difference between those two. All right, so that's what we're looking at here. So I'm going to subtract the area bounded between x equals b and x equals 0, and x equals a and x equals 0, those two regions, and what I'm going to end up with is the area in between the two. All right. Sort of a roundabout way of getting across probably a simple idea. Terrible diagram, but when I zoom out, it looks gorgeous. Not really sure why I put the diagram here for the second one, if I'm going to come back to it later, so I'm just going to kill that. All right, so apologies for anybody who drew that diagram in advance. Okay, so property number 1, if f is defined as x equals a, at x equals a, then the integral on the interval from a to a of f of x dx is equal to 0. Right? And all that's saying is that if I'm going from A to A, I will accumulate no area. Poor quality arrow. All right, so no area accumulated. Number 2, if f is integrable on a to b, then, and this is kind of a weird one, the integral on the interval of b to a of f of x dx is equal to negative the integral on the interval from a to b of f of x dx. All right, so reversing the limits of integration reverses the sign. All right, so I'm just going to kind of oversimplify this a little bit. So I'm going to draw a rectangle. Just a simple rectangle. If I wanted to find the area, I would have some height multiplied by some value for the base. All right, so the area would be b minus a times h. Fairly simple. Now, if I were to go the other way, so let me draw a new diagram. I'm going to change some things up though. So same height, but now I'm going to swap the bounds of integration. That's going to make this a minus b. And that's going to make this, in parentheses, a minus b times h. All right, so what we're looking at here are opposites. All right, a minus b is the exact opposite of b minus a. All right, so that's all we're looking at there. All right, swapping the bounds of integration, we'll swap the sign of integration. Additive interval property. I think this one's a little bit in the realm of common sense. So if we have an integral on the interval of a to b, and then we create some value c that's in between a and b, what we'd be looking at is the sum of those two areas. All right, so I think that falls, like I said, squarely in the realm of common sense. Number 4, we have the constant multiple rule, which is really saying, I mean, I'll oversimplify it, but I'll basically say double the height, double the area. Triple the height, triple the area. Half the height, half the area. Because f of x is representing the height. And so if we're taking the area of a region where one component of that area is going to be the height. All right, so base times height. So if you double, triple, quadruple, multiply by 10, one dimension, you're going to multiply the area by that dimension. All right, so that's all the constant multiple rule is saying. So I didn't include a diagram for that. Pardon me, additive function property. It's saying that if I want to add or subtract two functions on a closed interval from a to b and find its area, which is really what a definite integral is saying, then what I can actually do separately is find the areas of each one individually and subtract or add the two individually. All right, so I have my arbitrary function here, which I'll call f. So I'm going to create a brand new arbitrary function, which I'm going to call g. So unique. All right, so f is going to have its own area bounded, but g is also going to have its own area bounded by a and b. So I got a little overzealous there. Let me do this using a technique I like to call the right way. You know what? Honestly, that is an Easter egg that I've been using for a solid 20 years. If anybody, and I mean anybody, gets that Easter egg, 5 bonus points. All right, so and honestly, I'm not even sure I'm getting the quote right. It could be a method I like to call the right way, a technique I like to call the right way. It's something in that neighborhood, I forget. But anyway, so back to the matter at hand. I have area under G, area under F. So if I wanted to find the sum of the two, what I could do is just take the red area and add it again upon the F area, which is the black area. Or I can take that red area, the G area, and subtract it from the F area. All right. So a couple of possibilities there. Preservation of sign. It's saying that if f is integrable and non-negative on the interval of a to b, so if f is positive, then the function will be positive. I don't know that this necessarily requires a diagram, but I'm going to do it anyway. Sorry, a little eyelash on the screen. So I'm going to just go with the rectangle approach again, like I did earlier. So let's just say I use a rectangle to estimate the area. This is going to have some value, some positive f. And I know it's positive f because it's above the x-axis. And this dimension here will be b minus a. Difference between two positive values is going to be positive itself. All right, so area guaranteed to be positive. Now, if the function was below the pardon me, the x-axis, then f would be negative, and that would make, assuming we're kind of living on the right-hand side of the y-axis, that would give us a function that is guaranteed to be negative, or area that's guaranteed to be negative. Preservation of inequality property. All right, I have a few little diagrams here. I'm not sure I need them all, but I kind of went a little crazy here. So we have A is less than, F is less than G. So let me make F and let me make G. F and G. Watch your mouth. right? So the bounded areas would necessarily be, or would necessarily have a corresponding relationship. So I do not need the third diagram. All right, so, and I think that makes sense just by looking at these two. So if I'm looking at f on the interval of a to b, f is I'll call it a lower function. It's got a lower height than g, so it's going to capture a lower area, or less of an area, if we want to use like correct grammar and stuff. So these are the fundamental properties. I don't want to overuse the term fundamental, but they're fundamental properties of a fundamental theorem of calculus. So, you know, it is what it is. But they're pretty important in terms of having an understanding of the material. But the reality is you can do a lot of this on your calculator using well, it's Math 9. So I'll pull that up in a sec. But it's really pretty basic on your calculator. But I did want to give you a little bit of an overview on how this stuff works the way it does, you know, at least by hand. So that being said, we have a couple of examples on the next page that do not give you a specific function. So we have to use the properties here. So example 1, we have on the interval of 0 to 6, I'm looking for the area bounded by the function f of x. But my addition property tells me that 0 to 6 is really the same as going from 0 to 3. And then going from 3 to 6. And they tell us in the open here that 0 to 3 has an area of 4, and 3 to 6 has an area of -1, and 4 plus -1 is equal to 3. So that's pretty not bad right there. Going from 6 to 3 is the exact opposite of going from 3 to 6. Right? So we can negate the integral and go from 3 to 6, f of x dx. So -1. Part C is my favorite, and I'm sure it's yours too. Maybe you don't realize it. Now you do. Good. Very good. Yep, it's 0. Sometimes it takes a second, but when it clicks, it clicks. You know, it's nice. And so when you see those lower and upper bounds being the same, you just kind of, you go after it like a beast. And it makes make it a world go round. Anyway, so in D, I see I have a constant multiple. So I'm going to pull out the -5. Integral on the interval of 3 to 6 of f of x dx. Now this is some side work that I'm showing for note-taking purposes. But do you got to show the notes? No. Just give me the answer. So -5, and we know that on the interval of 3 to 6, I have an area of -1, and we're looking at -5 times -1, which gives me a +5. All right, so I'm going to ask you to tackle the problems on pages 2 and 3. Now, I will say that example 2 is a little on the tricky side. So is example 3 and example 4 and example 5. Internal debate. I'm going to do example 2 right now. completely changed my mind right on the fly, right here, right now. All right. So what we're given here is a shaded area of 1.5. Now, they're telling us that it has an area of 1.5, but that can't be right. All right. Later on in the unit, we're going to learn about the difference between a net area and a total area. Area for A, because it's below the x-axis, that area has to be on the interval of 0 to 2 of f of x dx has to be equal to negative 1.5. All right, so I've been using an integral and area interchangeably in terms of the terminology, but we're going to find later on that they're not exactly the same thing. All right. They tell us that the integral on the interval of 0 to 6 is equal to 3.5. So what I'm going to do is I'm actually going to set up a little equation here. We didn't know we could do that, which is, yeah, why we're in this class. Very good. So we're going to take the integral on the interval of 0 to 2 of f of x dx, add to that the integral on the interval of 2 to 6 f of x dx, and that's going to equal the integral on the interval of 0 to 6 of f of x dx. All right, so we just discovered by adapting one of our properties that the integral on the interval of 0 to 2 is negative 1.5. I have no idea what the integral on the interval of 2 to 6 is. But they told me in the open that 0 to 6, the integral, is equal to 3.5. All right. So by solving this equation, adding 3.5 to both sides, I get the integral on the interval of 2 to 6 of f of x dx is equal to 5. All right. Now, why did I do that? Well, because I'm a savant. You know, like I just looked into the future and I was like, oh, obviously that's what I'll need to do. No, you know why I did that. I did that because I've done this problem 1,000 times before, and I know that that's something I need to do. How would you know to do that? Well, you wouldn't until you start investigating the nature of the question, and then you see, oh, wow, I think I might need to do something like that. All right, so I got it out the way initially. You might have done it a little bit down the line, but it all comes out in the end. All right, like for example, in A, oh, look at that. The integral on the interval of 0 to 2 is negative 1.5. That was the first thing I figured out. Didn't even know I needed to know that. Of course I did. All right, so 0 to 6 of bracket. Fancy looking bracket, but that's just another way of saying I'm grouping two expressions together. So I'm going to say the integral on the interval of 0, whoop, that is a poor quality 6. It was such an ugly 6, it looked like a 2, of 2 dx plus the integral on the interval of 0 to 6 of f of x dx. Now, 0 to 6 of 2 dx. Two ways to handle that, one much cooler than the other. So, this is a function, f of x. Well, we already used f of x. So y equals 2. Going from 0 to 6. Now again, the integral generally means the area between the function and the x-axis. So what, pray tell, is the area bounded between this function and the x-axis going from x equals 0 to x equals 6? Exactly. The area is going to be equal to 12. Very good. So I have a 12 here. Now, going from 0 to 6, they told us that was 3.5, so we already know that. So 15.5, final answer. Now, a different approach. Math 9. If you have a TI-84 with the correct software, because the most updated software is the correct software. If you don't have the updated software, then you can go to ticalc.org or send me a message, because there's no reason why you shouldn't have the most updated software. All right. You just type in the function 2, the bounds, overshot the Mac, as they say somewhere, and we get it. All right. Now, if you're kind of mind reading, you're going back to, like when I said one of these two methods is cooler than the other, much cooler, you're probably trying to guess which one that I would think is the cooler way. I think you already know the answer to that. So that's my second Easter egg for the video. So the cooler way to solve this problem, the integral on the interval of 0 to 6 of 2 dx. Send me a message. Let me know what you think the cooler way is. If your cooler way is the same as my cooler way, then you get a bonus point. And I'll leave it at that for now. Part C, it says the integral on the interval of 0 to 6 of the absolute value of the function. Now, this goes back, I mean, this is a blast from the past. This is something that I like to actually spend a lot of time on in Algebra 2 and Pre-Calc. And by a lot of time, I mean like an entire class period. Now, let that sink in for a second. Think about Algebra 2. Like, how often can you spend an entire class period on a topic? It's very rare. All right? So, the absolute value of a function. Now, we weren't given the equation of this function, but we were given a graph. Now, what I can do is I can just kind of ballpark it. All an absolute value function is it's really just taking the negative parts of the graph and making them positives. All right, so let me get a little kooky here for a sec here. Let me just move that out the way. Take screenshot. I'm going to copy it. I'm going to paste it. I'm going to zoom. And then I'm going to go red for those keeping score at home. All right, so the negative part of the graph becomes positive. Now, going back to the open here, we discovered that going from 2 to 6 gave us an area of 5. We also knew that region A had an area of 1.5, but it was negative because it was below the x-axis. All right, so now it's going to be positive. So this interval is going to have an area of 1.5, and this interval is going to have an area of 5. So all we have to do is take the sum of those two bad boys, and we get 6.5. And honestly, it was really because of that part of the problem, and for part E, that I made the executive decision to do this example for you. Part D is really just constant multiple again. We love constant multiples. Honestly, you think back to the beginning of the course, constant multiple was such like a foreign term where it was like, what the hell is this guy talking about? Now, hopefully, it's more like, I know what he's talking about, I think. Nah, you know what I'm talking about. It's a constant multiplier. It's a value that you're multiplying a function by. All right? So you can multiply a derivative by that same value, antiderivative, a limit. Right? There's so much you can do with it. That's why the greatest common factor was so important way back in Algebra 1. All right? Negative 2 times negative 1.5 gives us the result of 3. Now the average value, it's kind of a throw-in topic. It's like if I were to tell you that the area over the interval, and again, we know the net area over the interval of 0 to 6 of the function f of x dx was equal to 3.5. Okay. So if I were to tell you, and really if you're thinking about net area, net gains and losses, snowfall is the first thing that might come to mind. I don't know if you're a teacher or student, maybe that's the first thing that comes to mind. If you're like me in any way, shape, or form, that's definitely the first thing that comes to mind. So at the end of a month, I tell you that the net amount of snow on the ground is 12 inches. What that means is that snowfall happened, right? So we had some snowstorms, we had a thaw. The snow fell, it accumulated, it thawed, it accumulated again, it thawed again, and at the end of the month, there were 12 inches of snow on the ground, right? Not typical for New York, but let's say we're not in New York, right? Let's say we're in Vancouver, right? So if I were to tell you to find the average of that, the first thing you're probably going to do is, all right, well, let me take that number and divide it by 30. 31, 29, whatever number of days there were in that month, all right? That's all an average value is. It's taking that number and dividing it by the interval over which the accumulation occurred. Right? So I'm taking that 3.5 and I'm dividing it by 6. All right? So 3.5 divided by 6. We got that lovely looking decimal. I'm going to math frac that. So we're looking at about 7/12. Oh, we're looking at exactly 7/12. All right, now page 3 is something that you can do entirely on your calculator, but I want you to take a little bit of time, draw a sine wave, all right? So now, drawing a sine wave is as simple as saying y equals the sine of x in your calculator. For you, it's a little easier, actually, than my awesome calculator here. All you have to do is sine of x and then zoom 7, zoom trig. bring up this graph and work off of that. Just one period of this graph going from 0 to 2 pi will get the job done. All right. So let me just get it looking like a 2 pi. That'll allow you to tackle your way through all of these problems. But like I said, you can use Math 9 to get the job done, but try not to do that, at least in the early going, because I'd like to see if you could use the properties. All right. So your only challenge at this point is to just tackle page 3. All right.